Okay, I'll go over quiz 4. We have an ideal gas having a molecular weight equal to 44 and a CV, constant volume heat capacity, equal to 0.16 BTUs per pound degree Fahrenheit, or pound degree Rankine. Initially, question 1, it's contained in a piston cylinder arrangement. So here's your piston cylinder arrangement, and your gas is in there, and it's compressed. So we're putting work in isothermally, so T is constant at 100 degrees Fahrenheit, or 460 degrees Rankine, and its initial pressure is 14.7. So it's compressed to 1/2 its original volume, state 2. Piston's gone down, and V2 is equal to 1/2 V1. So the work is the integral of P dV is equal to the integral of m over molecular weight RT over V dV. What we're doing is solving for P in terms of V and T. We can take part of this outside the integral. So all these values are constants because it's isothermal. Isothermal means the temperature stays the same, so it's 460. Excuse me, that's 560. 560 degrees Rankine. At the end, 100 degrees Fahrenheit, 560 degrees Rankine. So there's your work, and we'll take that to be the mass was given. We want to find the work per pound mass, so we'll take 1 pound. 1 pound mass divided by the molecular weight, 44 pound mass per pound mole. Let's see, that's times R. And here we've got to be careful with the R. We want this answer in BTUs, so we'll use the R of 1.987 BTUs per pound mole Rankine times the temperature, which is 560 Rankine. All of that's times the integral. Let's put times the integral of dV over V. And that integral comes out to be ln of V2 over V1. And this is, by the way, the work out. If we want the work in, it's negative the work out. So we can switch the order of integration. Roll down. And that becomes work in equals m over molecular weight RT ln of V1 over V2. So we've taken the minus sign and flipped these ln of 1 over a number is minus ln of that number. So this comes out to be, when we put all our numbers in, we come up with 1.987 over 44 times 560 ln of 1 over 1/2, which is ln of 2. And that whole thing comes out to 17.5 BTUs. Okay, part 2 of this problem was we took a tank and put that same gas in the tank. We don't know how much of it we put in there. We have a 5-foot cube tank. The pressure is 14.7 psi, and the temperature is 100 degrees Fahrenheit, which is again 560 Rankine. So M equals PV molecular weight over RT is equal to 14.7 times 44 times the molecular weight, times the volume is 5, divided by R, 10.73, because now we're dealing with PSI and feet cubed. And then times temperature, which is 560. Come out with a mass that we had in there of 0.538 pound mass. Now the delta U, the energy balance, is in equals out plus accumulated. Now there's no work coming in or out because it's a tank. It's not moving, the boundary's not moving, so there's no work in or out. We're adding heat to the tank. So N is 0. N is Q, Qn. Out is 0. Accumulated is delta U, which would be M times delta U, lowercase, which is equal to the mass, 0.538 pounds. Delta U for an ideal gas is CV delta T, so that's 0.16 times T2 minus T1. Now you were told in this case you wanted to double the pressure, so state 2, draw it over here, state 2 has the tank with double the pressure. So P2 equals 2P1. And so the volume density, P is PV equals RT. So these all constant, P proportional to T. So the temperature also must have doubled. T2 equals 2 T1. So this would be 2 times T1, which was 560, minus T1, which was 560. And that whole thing, when you multiply it all out, comes out to a total Q of 48.2 BTUs. So there's answer to question 2. Now questions 3 and 4, you were asked to find the work and the heat interaction for this situation. We started with 1 foot cubed, a piston cylinder device with 1 foot cubed volume. Put refrigerant 134A in it, and the initial conditions were we have 1 pound mass, so that your initial volume V was V1 equals 1 foot cubed per pound mass, and you were given the initial temperature was 20 degrees. Now you find that it must be saturated because V of 1 foot cubed is greater than Vf and less than Vg at 20 degrees. So we can solve for the quality to find out our initial condition. So V1 is equal to 1 feet cubed per pound mass equals 1 minus X. Vf, which is 0.01207, plus X Vg, which was 1.408. 1.408. Solve for X, and you have X at state 1 is equal to 0.708. Now you plug that in to find U1 is equal to 1 minus X UF plus X UG. Plugging in the numbers from 20 degrees Fahrenheit, you wind up with U1 is equal to 74.25 BTUs per pound. So now we have state 1 specified. We also know that at 20 degrees P sat equals 33.15 psi, psi-A. And so we have this piston bearing down. We said it was a frictionless piston, so I'll indicate that that's well lubricated. And we're going to rise that piston, weighted piston, such that as it rises it has the same weight, so the pressure is going to stay constant. So this is a constant pressure process, and the work is equal to integral of P dV. P goes outside the integral, is equal to P times V2 minus V1, that's work out, equals P M times P times lowercase v2 minus v1, specific volumes. And we were told that m is equal to 1 pound mass. So our work then becomes, we have to find v2 in order to find the work. However, we know, since it's a constant pressure process, as this piston rises, let's indicate this piston having risen up here a little bit. This piston will rise. It's saturated. It'll stay saturated, and it'll stay at the same temperature until it's all vaporized. So we know that it must have all vaporized because the final temperature is now 40 degrees Fahrenheit. So it heated up. It must now be in the superheated region. So I'll go to another page and we'll look at those properties. We know now that the temperature is 40 degrees and the pressure is the same pressure it was before, 33.15 psi. So go to another page and we find that at state 2 we have to interpolate to find the volume. The volume between, we interpolate between 30 and 40 psi in the table. So to do this, between there I'm 33.15, so that's a fractional distance of 0.315 between those 2 points. So the volume at 2 is equal to 0.315, taking data from your table, 0.315 times 1.213 minus 1.653 plus 1.653, that's how you interpolate, is equal to 1.51. A similar interpolation on internal energy at state 2 gives you U2 equals 101.0. Okay, now we can do our work calculation. Work is equal to MP times V2 minus V1. And then I have to multiply by this 0.185. That's going to get it into BTUs. That's BTUs per PSI feet cubed. And that comes out to a work of, let's see, 1 times 33.15 times 1.51, the new volume minus the original volume 1, times 0.185 equals 3.13 BTUs. And the energy balance then is in Q equals out. Switch back to Q equals out. Work is going out plus delta U, that's the mass, 1 times U2, 101, minus U1, 74.25. Substitute in for the work was 3.13. And we come up with our total Q is 29.8 1.9 BTUs. That covers quiz number 4.